Welcome back to another explainer. Today we're diving into the fascinating, completely invisible armor that protects our digital world, Reed-Solomon codes. You know, if you really stop to think about it, digital data is incredibly fragile. It's just ones and zeros flying through the air or sitting on a piece of plastic, constantly getting bombarded by noise, scratches, and interference. And yet somehow our movies stream perfectly, our deep space probes send back crystal clear images, and our files don't just randomly corrupt. Today we're going to unpack the brilliant mathematical safety net that makes all of this modern technology possible.
Here's a quick look at our roadmap for today. We're going to cover the digital error problem, meet Reed-Solomon codes, break down the anatomy of a code word, look at decoding and coding gain, peek at the underlying math, and finally wrap up with hardware versus software. Section 1. The digital era problem, or the perilous journey of data. To kick things off, we really need to understand just how hostile the environment is for our digital data. It is a bumpy ride out there.
Think back to the days of physical media, maybe an old DVD you've still got lying around. Have you ever wondered how a completely scratched up disc with visible damage still plays skip-free audio and video? Or how a noisy, weak signal from a cell tower miles away somehow hits your phone with perfect clarity?
Well, the secret is this massive, ubiquitous digital safety net running constantly in the background. We're talking deep space satellite communications, digital TV, high-speed internet modems, right down to the barcode scanner at your local grocery store. It's literally everywhere, quietly fixing mistakes before you even realize they happened. Moving to Section 2, meet Reed-Solomon codes, the hero's armor. Let's officially put a name to this invisible shield. We call them Reed-Solomon codes. They're a specific type of block-based linear error-correcting code, essentially digital armor. They take a block of your data, slap some extra redundant bits onto the end of it, and use that mathematical extra baggage to perfectly rebuild the original data if it gets smashed up in transit. They don't just spot errors, they actively fix them. Section 3. Anatomy of a code word, building the armor. Let's look at exactly how this data gets bundled up to protect it. Take a really popular configuration of this code, RS-255-223. Imagine a block of data that is exactly 255 bytes long. We slice that into two chunks, 223 bytes of your actual, useful information, the stuff you actually care about, and 32 bytes of protective parity symbols. Those 32 bytes, that is your armor. The real magic is in the recipe here. N is our total length, 255. K is the data, 223. S is the symbol size, which is 8 bits or 1 standard byte in this case. But check out T at the bottom. T represents the number of correctable symbol errors. Since we have 32 bytes of parity armor, which the math defines as 2T, the decoder can automatically fix errors in up to T symbols, meaning the system can magically reconstruct up to 16 completely corrupted bytes, no matter where they happen to be in that 255-byte block. Pretty wild, right? And what's super interesting is that these are systematic codes. You'd think error correction means scrambling everything into a totally unreadable mess, but nope. The original 223 bytes are completely unchanged. They're sent plain as day, with that safety net trailing right behind them. Engineers can even artificially shorten these codes by padding the front of the data with imaginary zeros, crunching the math, and then just skipping the zeros during transmission. It makes the whole system incredibly flexible. Section 4. Decoding and Coding Gain, the battle against errors. Let's step out onto the battlefield and see this defense mechanism in action. First off, we need to talk about the difference between a normal error and an erasure. A regular error is a total mystery to the decoder, but an erasure, that's a known casualty. Often, the receiving hardware, the demodulator, knows exactly when it got hit by a spike of interference, so it basically flags that specific symbol as bad. And because it already knows the location, a Reed-Solomon decoder can fix exactly twice as many erasures as it can random errors. So in our previous example, instead of 16 random errors, it could fix 32 known erasures. So when the damaged data actually hits, the decoder fights back in 4 highly calculated steps. First, it calculates syndromes. Think of these as mathematical symptoms caused strictly by the errors, not the data itself. Second, it builds an error locator polynomial, using some heavy-duty algorithms like Berlekamp-Mossy or Euclid's. Third, it runs a chain search to find the roots, pinpointing exactly where the errors are hiding. Finally, step 4 uses the Forney algorithm to compute the exact values needed to fix them. It is an absolute symphony of automated math. After all that intense number crunching, you only get 3 possible outcomes. Outcome 1, a triumphant recovery where the original data is perfectly restored. Outcome 2, a detected failure. The decoder basically raises a white flag, says, "There are way too many errors here, I can't fix this," and triggers a warning. But outcome 3 is the nightmare scenario, a silent misdecode. The errors accidentally align to look like a perfectly valid but completely different piece of data, and it passes it along with 0 warning. Thankfully, engineers designed these systems so that third option is statistically incredibly rare. So why go through all this trouble? Well, the ultimate prize of this whole process is something called coding gain. This is the massive, real-world physical payoff for all that abstract math. To understand why coding gain matters, let's say you're building a digital communication system, like a satellite link, and you have a strict target, a bit error ratio of 10 to the negative 9. That means you can only tolerate 1 bad bit out of every billion bits sent. Option A is the brute force method. Just massively crank up the raw physical power of your transmitter to shout over the noise. But that's incredibly expensive, it runs hot, and it eats power. Option B? Add forward error correction, like Reed-Solomon. This lets you hit that exact same 1 in a billion target while running your transmitter at a much safer, lower power level. That massive chunk of saved power? That is your coding gain. Section 5. The underlying math. Just a very quick peek under the hood here. I promise we won't get bogged down in the equations. Interestingly, standard general-purpose computer processors actually struggle with Reed-Solomon codes out of the box. Why? Because it doesn't use normal everyday math. It relies on finite field arithmetic, also known as Galois fields. Think of a Galois field like a closed-loop mathematical universe. If you add, subtract, multiply, or divide any 2 numbers in this field, the answer magically wraps around and stays inside that exact same predefined set of numbers. To pull this off quickly, computers usually need dedicated lookup tables and custom logic. The linchpin of all this is the generator polynomial. It acts almost like a secret password. Every single valid piece of data encoded with Reed-Solomon has to be perfectly divisible by this unique polynomial, often called gx. If a block of data shows up and doesn't divide perfectly by gx, the system instantly knows there's an anomaly, and that 4-step battle we just talked about kicks right into gear. All right, Section 6, Hardware versus Software. Manufacturing the code. How do engineers actually put this into our everyday devices? Because software historically choked on that intense Galois field math, engineers traditionally leaned hard on hardware. You'll find Reed-Solomon baked right into off-the-shelf standard chips. But today, the modern trend is using synthesizable logic cores, written in languages like VHDL or Verilog. Engineers just drop these logic cores straight into massive custom chips, FPGAs or ASICs, building an entire system on a chip that crushes the math at physical speeds way beyond what traditional software could ever do. But what happens if you do try to force it in software? Well, an old benchmark on a 16 MHz PC shows the brutal trade-off. With RS-255-251, you only have 4 bytes of parity armor. It's really light, and the processor zips through it at 12 megabits per second. But as you increase that armor to 32 bytes, like our RS-255-223 example, to fix more errors, the processor hits a brick wall. The decoding speed absolutely plummets to just 1.1 megabits per second. Heavy protection requires serious processing horsepower. And that brings us to a pretty provocative thought. From the scratches on a vintage 1980 CD to the incredibly faint signals of modern deep space probes, Reed-Solomon codes have quietly held our digital reality together. But as our digital footprint explodes and we sprint toward the quantum computing era, what new shapes will this invisible mathematical armor need to take to protect the unimaginable volumes of data of tomorrow? Thanks for joining me on this explainer. I bet you'll never look at a scratch disk or a satellite dish quite the same way again.